Let us examine the go back N ARQ protocol. So go back N is a fundamental protocol for ensuring reliable data transfer over unreliable communication channels. Go back N is a form of pipeline protocol that enhances efficiency by allowing a sender to transmit multiple data packets sequentially without waiting for individual acknowledgements. This approach, however, introduces specific trade-offs that we will analyze through a visual simulation. The protocol operates on two primary components, a sliding window at the sender and a simple buffer at the receiver. The sender's window defines the maximum number of unacknowledged packets that can be in the transit. The receiver, in contrast, maintains a strict order, only accepting packets that arrive in the correct sequence. Any packet received out of order is discarded, and the receiver's response is a cumulative acknowledgement. Acknowledgement confirms the last packet received in the correct sequence. If a timeout occurs before an acknowledgement, the oldest unacknowledged packet, the sender assumes the packet has been lost and initiates a retransmission of the packet. All the subsequent packets will also have to be retransmitted. So let me show you a packet loss scenario. We will now observe the go back N protocol, specifically addressing a scenario involving packet loss. The sender prepares 5 data packets labeled P0 to P4. The sender's window size is set to 4. The window opens, allowing the transmission of the first 4 packets P0 to P3. A timer is simultaneously activated for the first packet in the window P0. Packets P0 and P1 are transmitted from sender to receiver and are successfully transmitted. Upon arrival, the receiver will acknowledge them. The receiver accepts P0 first, as it is the next packet expected. It sends a cumulative acknowledgement ACK0. Similarly, the receiver accepts P1 and sends ACK1. The sender's window advances as each acknowledgement is received, but the timer for P0 remains active as it is the oldest unacknowledged packet. The sender, observing that the window has advanced, is now able to transmit P4. Now you can see packet P2, which was transmitted earlier, is lost in transit. So this is a event that we will be looking at carefully. As the receiver's strictly ordered acceptance policy will come into effect, P3 and P4, though delivered correctly, will be discarded. So packets P3 and P4, which were sent after P2, arrive at the receiver. Because P2 was lost, P3 and P4 arrive out of order. So receiver does not store them. For each discarded packet, the receiver sends a duplicate acknowledgement ACK1, informing the sender that P1 was the last packet successfully received in the sequence. The sender, having received multiple duplicate acknowledgements and without having received an acknowledgement for P2, reaches its timeout. The timer for P2 expires and will trigger a recovery mechanism. The sender assumes that packet P2 was lost and initiates a retransmission of not only P2 but all subsequent unacknowledged packets in the window. So P3 and P4 will also be retransmitted. The retransmitted P2, P3 and P4 arrive at the receiver. This time P2 is the next expected packet. The receiver accepts it and sends ARQ2. The receiver then accepts P3 and P4 and sends cumulative acknowledgements for P3 and P4. This signals to the sender that all packets up to and including P4 have been received correctly. The sender processes these final acknowledgements, advancing its window to include all delivered packets. Now the transfer is complete. Thank you.